I can start like that. I will put it down. So we are supposed to analyze NMR relaxometry data, which we collect as a part of our project. And today I would like to explain you what the relaxation dispersion data actually mean, what kind of information they include, and how to extract the information, not recursing to very advanced mathematical models. This would be the first goal. And after that, depending whether you will like it or not, whether you will have any questions, we will adjust the talks in such a way so they really become useful for you. But please, it's very important for me that we interact with each other. So please interrupt me anytime, please ask any questions, tell me explicitly that this is boring or whatever, because it's really meant for the profit of all of us. And as you know, I'm a physicist, I spend a lot of time working on NMR relaxometry, so some things might be easy for me, but far from being obvious for people who have different expertise. Okay, so first something which you know very, very well, but I would like to repeat it. Here you have collection of water molecules. Please do not think that NMR relaxometry is about water, although actually for food products, it very often is. However, here I draw water molecules only to give you a kind of illustration about how magnetic resonance relaxation works and what is the principle of this process. So water molecules are very good examples. They include 2 hydrogen atoms. And as you might know, in NMR, one speaks about NMR active nuclei. NMR active nuclei means nuclei which possess magnetic moment. And actually, hydrogen nuclei are NMR active. They are just single protons, and protons possess magnetic moment. In a quite naive way, you see here, I indicate the magnetic moments in blue. If there is no magnetic field, we do not apply any magnetic field. We just take a glass of water and whatever glass of any other molecules, let's say, which include hydrogen atoms. The magnetic moments are distributed completely random in all possible directions. This means that the total magnetic moment is 0. Then we apply magnetic field, and a miracle happens. This is a beautiful manifestation of quantum physics. Actually, the magnetic moments are allowed to take only 2 orientations in the magnetic field. They can be parallel or anti-parallel to the magnetic field. That's it. Now, okay. However, one can imagine that actually when the magnetic field is relatively weak, actually the preferences to be oriented parallel or anti-parallel to the magnetic field are not very strong. In principle, the molecules almost do not care. When the magnetic field gets higher, the preferences are well defined. And they are defined by so-called Boltzmann distribution. According to the Boltzmann distribution, which describes the fundamental law of our world, each system wants to take a minimum of energy. So the magnetic moments interact with the external magnetic field. And depending on the orientation, the energy of the interaction is lower and higher. Does not matter at this moment which one is preferred, whether the energy is lower for parallel or anti-parallel orientation is not of importance at all, and I never remember. I would need to think about the sign of some quantities. The point is that one orientation is associated with lower energy than the second one. When the magnetic field is low, the difference between the two energy levels is small also. When the magnetic field is high, the difference is much larger because it's proportional to the magnetic field. And the so-called Boltzmann distribution describes the probability that a state of a given energy is occupied at a given temperature. And of course, the probability of the lower energy level being occupied is at high magnetic field much higher than for the high energy level. So one observes significant difference in the population of those two energy levels. And the difference leads to magnetization of the samples. So of course, if we take, for instance, 1 cubic centimeter of water, you can easily calculate how many hydrogen atoms you have there. Actually, this is what we will be doing. And this is a lot of them. However, to give you an example, let's assume that we have 10 in total. And let's say 7 is oriented parallel, 3 is oriented anti-parallel. It means the difference is 4, yeah? And the difference contributes to the effective magnetization of the sample. So when we put a sample containing hydrogen atoms in a magnetic field, we create magnetization. Higher magnetic field means higher magnetization. Lower magnetic field, lower magnetization. Now, okay. So let's assume that we created a magnetization. This is called polarizing the sample. Then we change the magnetic field. We can reduce it, or we can increase it. But let's assume that we increase it. But this is just only for your attention. The same will happen if we decrease it. What happens? The system will repopulate. I mean, if the magnetic field is higher, the difference in the populations of those two energy levels also gets higher. So some of the magnetic moments must reorient. Or thinking in terms of quantum mechanics, the quantum state must change. And this is what is happening. However, this process takes time. And if we increase the magnetic field, slowly, I mean, what slowly means is another story. But let's say slowly, step by step, the system adjusts to the new equilibrium. It means the difference in the populations of those two energy levels becomes higher, and consequently, the magnetization becomes larger. And this is what you see here. Time is pending, and the magnetization gets larger, 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 and eventually the equilibrium in the higher magnetic field is reached, and the system does not evolve anymore. And the process of reaching the equilibrium is called relaxation. It is like a term from maybe philosophy, yeah, one could say. That reaching equilibrium means relaxing. Yeah, one can apply it to different areas of our life. However, here it means that eventually the system repopulated and achieved the populations according to the Boltzmann distribution in the new, in this case, higher magnetic field. And the evolution of the magnetization is very often exponential. Actually, we like when it is not exponential, because we think then that we discover a lot of interesting things, but then when it comes to a quantitative analysis, it becomes problematic. However, let us think for a while that it is exponential. Actually, if you ask me, for water in bulk, this process takes about 2 seconds. So it is very, very slow from the perspective of NMR relaxation. And then the characteristic time constant of this curve, if you fit it as an exponential function, the characteristic time constant is called relaxation time. And its reciprocal value is called relaxation rate. So this is the principle of NMR relaxation. Now about NMR relaxometry. To give you an idea, you polarize the sample, you reduce the magnetic field, the magnetization decays. You record the magnetization curve, you feed it, and you extract the relaxation time. Then you again polarize the sample, you again reduce the magnetic field, but to a lower value, to a different value than the previous one, and again measure the relaxation, and again. And thanks to the fast field cycling technology, we can vary the magnetic field in a very broad range, almost 4 decades, which means that we can collect relaxation rates at different resonance frequencies. And here is the trick, because people usually do not explain what the magnetic field has to do with the resonance frequency, or do not explain it in detail. You see, I told you that actually there's a gap between the 2 energy levels, difference between the 2 energy levels corresponding to the parallel and anti-parallel orientation of the magnetic moments. And I said also that the gap, the energy difference, is proportional to the magnetic field. Yes. But then one can say in this way. For sure you heard about Planck and so-called Planck constant. Yeah, H or H bar if the Planck constant is divided by 2 pi. The point is that according to this concept, energy can be described in frequency units. So energy is just the Planck constant times frequency. And this is how we arrive at the concept of resonance frequency. Namely, we have the energy gap. The energy gap is proportional to the magnetic field. Then the energy gap can be expressed in frequency units, which means that the frequency, called resonance frequency, is proportional to the magnetic field. So we get linear relationship between magnetic field and resonance frequency, which is nothing else like the energy difference in frequency units. And the proportionality constant is called magnetic factor. It is characteristic of each nuclei. So this is different for protons, different for fluorine nuclei, and so on and so on. Resonance frequency is equal to magnetic factor times the magnetic field. So thinking in terms of resonance frequency is like thinking in terms of varying the magnetic field. Okay. Here you have typical examples of relaxation data, of relaxometry data. For very simple systems like propylene glycol or glycerol. And here you see you have on the x-axis, you have frequency in hertz. It's just the resonance frequency. So we could if one prefers, but in our community one does not do so, one could also plot here magnetic field. And actually for protons, there is a well-known relationship. It's worth to remember that 42 megahertz corresponds to the magnetic field of about 1 Tesla. Now, okay. And here you have relaxation rates and reciprocal relaxation times at different resonance frequencies. It means different magnetic fields. So the curves usually look in such a way. Here you have example of some analysis. We'll come to that. You see that one can fit the curves nicely, decompose into something. So it means that there is some science behind, and maybe one could get some useful information from that. But the point is that everybody knows that NMR relaxation, NMR relaxometry gives information about molecular dynamics. But the point is how? What those quantities have to do with molecular dynamics? One can accept that the magnetization evolves because we change the magnetic field. Great. Okay, we can accept that it takes some time. Also great. Okay, the time is called for a kind of strange reason which nobody can understand at this stage, spin lattice relaxation time or rate. But what has it to do with dynamics? You see, if you think in this way, those two energy levels, one of them lower, one of them higher, it's easy to say that the system repopulates, so the populations of the energy levels change. However, this requires exchanging of energy with something. The system needs energy to repopulate, or the system needs to release energy to its surrounding. In case some magnetic moments come to the lower energy level. Because otherwise, if there would be no exchange with the surrounding molecules, ions, nuclei, and so on, it would be not possible to change the populations, yeah? Because if, for instance, this proton is supposed to change the orientation of its magnetic moment, it has to take energy from somewhere. Or this one, if it wants to invert, it needs to release the energy. And there must be something which accepts the energy. And this something, the other NMR active nuclei in the surrounding, and the collection of the nuclei is called lattice. Therefore, spin lattice. Spin is actually a quantum mechanical quantity to which the magnetic moment is proportional. So spin of this nuclei exchanges energy with other neighboring nuclei, forming lattice. So therefore, spin lattice. Yes. Now, how this exchange of energy takes place? There must be a kind of coupling between the interacting nuclei, yeah? The neighboring nuclei. And actually, in the case of protons or fluorine nuclei, the coupling is provided by magnetic dipole-dipole interactions. So one could say in this way, the magnetic moments interact not only with the external magnetic field, but they interact also with each other. So this one interacts, for instance, with that one within the same molecule, but this one also interacts with that one or that one belonging to different molecules. They're like, yeah, magnetic moments, like two magnets interacting with each other. The point is that the interactions fluctuate in time because of the motion. Hello? Was there a question? Okay, I do not hear, so I will continue. So there are magnetic dipole-dipole interactions between the nuclei, and the exchange of energy goes via those interactions. And those interactions fluctuate in time. For instance, this coupling within one molecule fluctuates in time because of rotation of this molecule. The coupling between different molecules, like here, fluctuate in time because of translation and rotation of those molecules. So there are different origins of the fluctuations. And now, the strength of the interaction, the time scale of this interaction, and the mechanism of this interaction, whether this is translation motion or rotation motion or something else, determines the efficiency of the repopulation. In terms of quantum mechanics, it determines the probability of spin transitions between different energy levels. And using the simpler language, the efficiency of the repopulation determines the relaxation time. If the efficiency is high, let's say this is not really a very scientific term, but quite intuitive. If the process of exchanging the energy is efficient, the relaxation process will be faster. The system will reach its equilibrium faster in a shorter time. So the relaxation time will be shorter and consequently the relaxation rate higher. So analyzing the relaxation rates, and specifically at different magnetic fields, different resonance frequencies, one can get information about the molecular motion. Actually, why it is so important to perform the experiments versus frequency? Because in classical NMR experiments, one usually performs experiments at one frequency, relatively high, 400, 500, 600 megahertz, and so on. Here we see we reach, for instance, from about 10 kilohertz to, let's say, 20 megahertz. So the frequencies are relatively low. The point is that not going deeply into spin relaxation theory, however, according to the theory, at a given resonance frequency, for instance, 1 megahertz, the most efficient relaxation process is associated with a motion which occurs on a time scale matching reciprocal of the frequency.
Danuta, can I ask a question?
Sure.
What should we understand from the most efficient relaxation?
I would put it here, yeah? For instance, here we decompose a relaxation curve like that. It's actually for glycerol into two contributions. Anticipating the results, which will come to this later, this contribution at low frequencies is associated with translation, and this one is associated with rotation. And if you take a spherical molecule, according to the Stokes-Einstein equation, there's a relationship between a time scale characterizing translation dynamics and rotation dynamics. And according to that, for perfect spherical molecules, the ratio between the characteristic time constant is 9. So let's say 10, yeah, order of magnitude. In practice, it's like more like 50, 60 instead of 10. However, the translation dynamics is slower, let's say. And what happens here? Actually, one should treat it with a kind of approximation. However, here is the range of lower frequencies. Here, let's say, is the range of higher frequencies. Yeah? And here what one could say, at lower frequencies, slower dynamics gives a larger contribution to the relaxation. At higher frequencies, faster dynamics gives the dominating contribution. And one should not read it so literally because it depends on complex spin interactions. However, generally one could say like that. It's not that I take, for instance, I don't know, 100 kilohertz, and then I say, so it's 10 minus 5, and then I say that the dominating relaxation process is of the order 10 minus 5 seconds. It's not like that. However, I would say lower frequencies, at lower frequencies, slower dynamics dominates the relaxation process. I don't know whether this is clear. Eventually, this is a kind of transition period.
Okay, thank you. Yeah.
It depends on the specific system. If you take the very simple equation for relaxation, which I will present in a couple of minutes, then one can generally say that, okay, the relaxation rate reaches its maximum when the time constant is equal 0.6 reciprocal resonance frequency. This comes from the math. But this is for the simple idealistic case. Generally, I want to say that at lower frequencies, slower dynamics manifests itself more as the dominating relaxation contribution. What you see here, yeah? I think. Is it clear?
Yes, thank you.
Okay, thanks. So let me continue. So, okay. Now it's something what is quite tricky. I know that this is a lot of curves here. However, here you have seen experimental curves. Now there is a little bit of simulations. Namely, if you look to very old books, like 50, 60, almost 70 years old, actually you do not remember probably something which is very famous, a Bragam book about magnetic resonance. Sorry. However, it was just something which, when I was a PhD student, we studied. Namely, even before Abraham, there is something what one calls BPP formula. And here you have so-called BPP formula. It links relaxation rate with dynamics. How? The BPP comes from Blomberg, Morgan, Powell, just abbreviation of first names of the people, abbreviations of the names of those people who derived those expressions. What this expression tells us? It assumes this expression is valid for very simple system, like for instance, isolated water molecule, just one water molecule. Because if one wants to develop something, one should start with something simple. And this formula was derived many, many, many years ago, just the beginning of NMR. And the trouble is that people still use it. Actually, I pay really tribute to the authors of this theory. However, it's absolutely clear that they had in mind just model system composed of two spin 1/2 nuclei, like two protons, two fluorines, or something like that. And there were also some other restrictions. What this formula includes. This is a relaxation rate at a certain resonance frequency. The resonance frequency is not in hertz, here is in radian per second, it's multiplied by 2 pi. Actually, it's worth to know that because of some normalization, I will not deal with this much. Actually, in all the expressions, we have Here the resonance frequency in angular frequency units, it means we multiply the frequency by 2 pi. Okay, so I told you the relaxation rate is larger when the relaxation is fast. So the relaxation rate is determined by the strength, the amplitude of the dipole-dipole interactions, and the amplitude is hidden here. This quantity is called dipolar relaxation constant, and it strongly depends on the distance between the interacting nuclei. It's like 1 over r⁻⁶. So it includes the strength of the interactions. So relaxation rate is proportional. Then there's a quantity here called correlation time, tau c. Well, the meaning of a correlation time is to some extent not clear. However, at this moment, one can say that this is a characteristic time constant reflecting the time scale of the motion. The first question which appears is actually which motion, because molecules perform a lot of motion. I would put it in this way. Nobody wondered about that at the stage when this theory was provided. It was the first relaxation expression. It was a great achievement. But if you want me to tell you which motion, I would say again, isolated water molecule and rotational dynamics. So I take 2 protons in a water molecule. I calculate the dipolar relaxation constant. Actually, it's not a very big deal to know the distance between 2 hydrogen atoms in water molecule. If you ask me what is the motion, I would say isotropic rotation of the water molecule. Or something like that. Something very, very simple. And the characteristic time constant of this motion. So this is the second factor, the time scale of the motion. The third factor, which I told you, is the mechanism of the motion. And where the mechanism is hidden, actually in the form of this expression. So it is a this function is called Lorentzian function. How? Here we have to say quite a lot about the relaxation theory. I will try to do it in an intuitive way. Actually, we can make a separated lecture about that, but I think you will get bored if I start again. According to quantum mechanics, to calculate the probability of transitions between 2 energy levels, one deals with a quantity which is called correlation function. Here one can again use our intuition. Correlation between something, yeah? So there is event, and whether it has any influence of a next event. Whether 2 things are somehow correlated. Here, what we correlate is a position, maybe not exact, generally saying is a position of a molecule. But for instance, if we look at rotating water molecule or any other molecule, what we are interested in, imagine that here we have a direction of the external magnetic field. And we draw a line between the 2 protons. And this line is called the 2 hydrogen atoms. And this line is called dipole-dipole axis. And at time 0, let's say now, there is a certain orientation of the dipole-dipole axis with respect to the external magnetic field. Then the molecule moves chaotically, rotates chaotically, around its axis somewhere here in all possible directions and planes. And after some time, we ask what is the orientation again of the line connecting those two hydrogen atoms. And the question is whether those two orientations, the initial one and the final one, are somehow correlated. Well, it depends, yeah? It depends how fast the molecule moves compared to the time we are talking about. Because if the molecules move on a time scale of nanoseconds, rotates on the time scale of nanoseconds, it's 10 minus 9. If I say, okay, now is my time 0, now after time much, much shorter than the correlation time, so let's say 10 minus 15 seconds, the orders of femtoseconds, I will ask whether the orientations of the dipole-dipole axis are somehow correlated. Everybody will answer yes, because actually the molecule did not have time to move much. So with very high probability, the orientation at the later time point is similar than at the initial time point, yeah? But if the time scale of the motion is again 1 nanosecond, and I ask after 1 second whether there is any correlation between the final and initial orientations, the intuitive answer will be no, because the system had a lot of time to forget what it was at the beginning, yeah? So this is somehow the concept of correlation function. And again, the form of the correlation function, its dependence on time, is determined by the mechanism of motion. However, deriving those equations, it has been assumed that the correlation function is exponential, a kind of exponential decay. So in time, just the system forgets its initial position. And this is the underlying assumption. Actually, I have to say that isotropic rotation of spherical molecules fulfill this condition. Indeed, the system is losing its memory in an exponential way. So this is a perfect case for like rotation of water. Now, we do not work in time domain. Actually, some experiments are performed in time domain. We have the time domain NMR. However, in NMR Relaxometry, we have not time, but frequency on the x-axis. So we apply something which is called Fourier transform, and this is mathematics here, and if you do not know what it is at this stage, do not bother. We'll also come back to that. However, we go from time domain to frequency domain. And the correlation function, after applying Fourier transform, gives something what is called spectral density. And actually, even today, I got a question from somebody what actually spectral density is earlier today, because it's often used in the theory of relaxation. It's nothing else like Fourier transform. As I said, if you don't know what Fourier transform is at this moment, does not matter. However, it's a kind of transformation of correlation function from time domain to frequency domain. And actually, from mathematical point of view, if the correlation function is exponential, the spectral density, I mean the Fourier transform, takes Lorentzian form, like here. So here the mechanism of motion, which in this case has been assumed is described by an exponential correlation function, gives this form of spectral densities. So this is the story behind this formula. And you can clearly see that it is far from, how to say, it's far from we observe in real systems. Okay, if this is clear, I would like to show you something. Here, I performed some simulations. So I just plotted this formula for different correlation types. Yeah, starting from quite slow motion to quite fast motion. And I plotted it up to 100 megahertz. No, up to 1000 megahertz, yeah? So it's 1 gigahertz. And what happened here? Imagine what is happening here. Let's assume that the correlation time is very short. So this product, omega tau c, is like almost negligible, especially if I take square of it. It's like almost zero. So this term is gone in the denominator. And this term is gone as well. So this whole expression converges to 5 times the dipolar relaxation constant times the correlation time. And when the correlation time is very short, this product is much smaller than 1, even for a large frequency. So you have the case here. The relaxation rate is frequency independent in a very broad range of frequencies, because almost until here, the product omega tau c, if tau c is 1 nanosecond, can be neglected compared to 1. So this expression becomes frequency independent. Only here for high frequencies, one can see that it bends down, so it shows a kind of frequency dependence. When the time is long, the condition that this correlation, that the resonance frequency times the correlation time is not so small, is fulfilled even at relatively low frequencies. Because look, for instance, here, the resonance frequency is 100 hertz, is 10 power 5. If I multiply it by 2 pi, it's approximately 10 power 6, yeah? It's approximately 10 power 6. If I multiply it now with the correlation time, it's 10 power 6 times 10 powers minus 6, so it cancels, so it gives around 5. If I square it, it's about 25, yeah? So obviously this term is important compared to 1, and you clearly see that the curve becomes sensitive to the frequency. And all the range between. So for instance, if you perform experiment and you see that the relaxation curve, the relaxation profile is almost flat, or is flat over a broad range of frequencies, it means the motion is fast. So this is a kind of thing to know, yeah? For instance, if you interpret your data and it comes out that you got shorter correlation time for such curve than for such that, obviously something is wrong. Because as long as the curve is flat, you can be sure that actually the correlation time is so short, so this product is considerably smaller than 1. If you look here, for instance, yeah, here is high temperature, whatever it is. And for some part, the curve is quite flat. At lower temperature, let's say one can say that up to this point is more or less flat. At lower temperature, definitely it's not, because the dynamics became slower. So this is something to think about. Then people sometimes do a trick. I'm strongly against this trick, but it can happen that you will find it. So I will explain it and I will tell you why I'm against this trick. This trick is called frequency temperature superposition, and I played it here theoretically, namely just on the simulated curves. What happened here? I multiplied the curves by omega, the resonance frequency. So here I have still the resonance frequency in logarithmic scale, as usually, because one can hardly show something in a scale when it covers so many ranges. However, here, instead of the relaxation rate, I have relaxation rate times the frequency. Yeah, relaxation rate times the frequency. And what happened? Those curves got maximum. It's very easy to figure out what I have done. I multiplied the relaxation rate with frequency, which means the frequency appeared here. Omega appeared here in the denominator. So the trick is that the product, the resonance frequency times the relaxation rate, is dependent now only on the product, omega tau c. It's not dependent separately on tau c and omega, but only on the product. So omega times tau c determines the shape of the curves. This brings us to the very simple concept. One will get the same curve if omega tau c is the same. But to ensure that omega tau c is the same, actually, in fact, I can vary both quantities. I can divide omega by 10 and multiply tau c by 10. The product will be still the same, and so on. And if you take into account that with increasing temperature, dynamics becomes faster, you have here the concept of frequency temperature superposition. Because, for instance, I increased the temperature, the dynamics became 10 times faster to make life easier. So the correlation time is 10 times shorter. So this curve will get the same value at 10 times higher frequency. However, it will look the same. So it's like I have this shape here. And all those next curves, for instance, this one, is of the same shape, but somehow shifted along the frequency axis. And of course, one can shift all those curves back, and then they will overlap into one. And sometimes such effect is called master curve in relaxation. The point is that, okay, if it is so, if you get your data, you play your experimental data, you play the trick, you multiply the relaxation data with omega, and you try to make this overlapping, and it works, it means that indeed it is so. However, I would never see this as assumption, because this concept assumes that the mechanism of motion does not change with temperature, only the time scale. So you see, for instance, if you have three-dimensional diffusion, which is completely isotropic in your system, and this concept assumes that even if you cool down the system very much, it's not that, for instance, the diffusion becomes more restricted or something like that. It still assumes that the molecules can freely move in all possible directions, but only slowly. So this is a kind of controversial concept. However, just so you know, people do such things, and it's worth trying to see whether maybe your system really behaves like that. Let me now, I promised you that there will be no math here. And you can skip this slide if you like. I only want to tell you. So here I explained the origin of this very simple formula, which to some extent describes rotational dynamics. But I told you that there are also dipole-dipole interactions between hydrogen atoms belonging to different molecules. And actually, those interactions fluctuate in time as a result of translation diffusion. And here the point is more complicated. Again, there are some formulas. The formulas are to some extent similar. You have here a function, you have here 4 times the function, here you have 3 factors. Here I have also function, I have 4 times the function. Here I have a kind of prefactor. I do not want to go into this subject right now. I only want to tell you that the form of the expression becomes much more complex in case of translation diffusion. There is a kind of integral here, and I know that it leads to a lot of difficulties. For instance, the typical question is, what is the U variable? Then I answer that this is a kind of integration variable. And of course, this thing is independent on U because the integration from 0 to infinity, it causes some confusion. We'll have a talk separately about those expressions and we'll go step by step. I just only want to tell you that such thing does exist. It corresponds to translation motion. And you see, for instance, that if one would try to apply this kind of formula for real systems, yeah, which perform translation dynamics, it would be disaster. Actually, this expression includes translation diffusion coefficient, which, not going much into the maths, is important to know. Actually, the translation diffusion coefficient is often called relative translation diffusion coefficient. It's like how fast the molecules move with respect to each other. So it's like relative velocity, yeah? 2 objects move, and what is the relative velocity? And of course, in case the motion is not correlated and the molecules are identical, relative diffusion coefficient is twice larger than self-diffusion coefficient. Because if I walk in one direction, you walk opposite me, our relative motion is twice faster than the motion of the separated persons, yeah, individual persons. So this is how it works. However, this also leads sometimes to a confusion. However, in case the motion is somehow correlated, so one molecule moves and it affects the movement of neighboring molecules, of course, the relative diffusion coefficient will be not twice self-diffusion coefficient. So this opens a kind of nice possibility to describe translation diffusion in food products. Actually, I have to tell you that maybe you know, but actually me and Messi, some of us together, in some papers, we made a series of papers in which we used NMR Relaxometry to investigate relative translation motion of water molecules in various food products. We didn't apply it so far to sugar products, but this thing is real. We'll come to that. However, what I would like to tell you now, let me only see whether I could, okay, I would need to leave this mode, but whatever. You see, there is a trick, because if you look at this expression, You say, oh my God, it's so complicated. I will need software for that and so on. Actually, we have software for that, and I would be happy to give this software to you. But it may happen that you can profit from NMR Relaxometry data in a simpler way. Do you remember this thing? When Messi asked me the question, what's that actually? I said that here we have relaxation dispersion profile for glycerol, and it stems from translational and rotational contribution. And this is the translational contribution, which is dominating at low magnetic fields. There's a trick. If the translation motion is fully isotropic, in this sense that the molecules move in all possible directions with the same probability, then if one puts on y-axis the relaxation rate and the x-axis square root of the resonance frequency, one should get a straight line here in the low frequency range. You can ask how long. I would say as long as the resonance frequency times the correlation time is much smaller than 1, because mathematically it stems from so-called Taylor expansion of the Fourier transform of the correlation function. However, if you observe such effect, it means that the motion is isotropic. And one can straightforwardly determine translation diffusion coefficient for the low frequency slope. So you perform linear regression, and from that you can get the translation diffusion coefficient. And this is what I will show you in a second. And we did such a thing for, this is a kind of complex expression. Okay, give me a second, maybe we'll see how it works. It's maybe worth to put this expression somewhere. Actually, I will make the whole presentation available to you. But it would be good to have it somewhere. I will think how to solve it in one screen. But before that, here you see that we tested this concept for very different systems, comparing diffusion coefficients obtained with this way with diffusion coefficients measured by gradient NMR methods, and the agreement is very good. Not going into detail, this concept is confirmed. I will show you this thing shortly. And just the last slide, although I have more, but I would rather prefer to stop at this moment and give you a kind of exercise, which we solve together because I think we do not have so much time. Here you have relaxation rate. Here you have resonance frequency. So a kind of typical representation. And here I plotted different kinds of spectral density functions. I mean, there are those functions which are here, yeah? Or here, so like this one. And for instance, this one is for isotropic rotation, the solid curve. So it takes such a shape. For isotropic translation motion, the shape is different. But you see, it can happen, for instance, that the translation diffusion is restricted to 2 dimensions, just between planes. We observed such a thing for some hyaluronic acid systems. Then there is also theory behind, and actually, in this case, it is expected that the relaxation rate will show linearity in the low frequency range when plotted versus the resonance frequency on the logarithmic scale. according to this expression. And you see it here. So there's a trick here. Why I'm showing that? Because before one jumps to a kind of analysis of the relaxation data, one should carefully first investigate the shape. The shape of the relaxation curve. The first thing which I would check is whether it shows a linear dependence on the square root of resonance frequency, because it means it's three-dimensional diffusion. Then I would keep in mind this figure, and I would try to see whether my relaxation data are more like that, or there's a linear curve here, because this tells a lot about the mechanism of motion. Before we jump to specific calculations, one can say a lot about what is going on. I might have problems with apply some mathematical formula and extract the time scales of the motion or the diffusion coefficients. But before we do that, we must have a kind of idea regarding the type of the motion, because otherwise we really do not know how to describe the system. If you allow me to stop at this moment, I would like to use like 15-20 minutes to solve a problem with you and give you a software, because which will be of use for you, I hope for the whole community, because it seems that I was talking like 1 hour. So Messi, if you allow me, let me stop at this moment. I would be happy to answer some questions. And then if you can still be with me, I would like to show you an example.
Hello, Danuta. I have a question.
Yes.
You mentioned the spectral density, yeah?
Sorry, I do not hear you.
Sorry, we are in the lab. I'm with Monica and Hatice.
It doesn't change.
We are in the lab. Yeah, I know. But you mentioned this spectral density, yeah?
Yes.
What it is? Can you explain it in the basic words? What is this spectral density?
As I said, it's Fourier transform of a correlation function, but I understand that this is not a kind of basic answer. So let me put it in this way. What is correlation function? First, I have two quantities. Depending on the kind of motion, the quantities can be a vector describing position of the nucleus, of the molecule. They can be, as in the case of rotational dynamics, the orientation of the dipole-dipole axis. I mean the axis connecting two hydrogen atoms. The quantities which we correlate depend on the nature of the motion. And then we ask ourselves the questions: with which probability I can guess the initial position, the initial value of this quantity, if I know the quantity after some time? And of course, if I know the quantity at the initial position, and you ask me what is the quantity of the initial position, it means after time 0, I will answer the question with 100% certainty. It's just the same. So the so-called correlation function will be equal to 1, yeah? Absolute full correlation of the final and initial values of the quantity. But then time is going. And after a very long time, compared to the scale of the motion, time scale of the motion, you ask me, you say, okay, you see, I look at the orientation of the dipole-dipole axis, and it is like that. It is 47.3 degrees with respect to the external magnetic field. Can you tell me what the orientation was 1 year ago. It can be any, yeah? Of course, I'm exaggerating this thing, but if the time scale is of the order of nanosecond, and you ask me what was the initial orientation 1 second ago, I will, of course, answer I have no idea at all. So then the correlation function will reach 0. If the time scale of the motion is 1 nanosecond, and you ask me after, I don't know, 2 nanoseconds, what was the initial position, I would say, okay, probably it was like here in this range, because, yeah, there must be still a trace of the initial position in the current one, because actually not so long time, after not so long time, but really, okay, I would have a kind of vacuum indication, yeah. So depending on how much time passed compared to the correlation time, the memory of the system about its initial situation will fade away, will decay. And usually, I mean not usually, let's say, because for instance, not for translation diffusion, but for isotropic rotation, the loss of memory is in exponential way. So if you have on the x-axis time, on the y-axis the normalized correlation function, which at time t equals 0 gives 1, you will have exponential decay. And then I perform Fourier transform of this exponential function, which actually Fourier transform is a kind of integral. So I would say, I take the function, I'll multiply it by cosines omega t, and integrate over time from 0 to infinity. If you like, we can make a kind of separated lecture about Fourier transform. However, from the conceptual point of view, is going from the time representation to frequency representation. If, for instance, I work with Leonid from Germany about time NMR, time domain NMR, we describe the effects in terms of correlation function, not spectral densities, because we do not transform to the frequency representation. So mathematically, it's just this Fourier transform of the correlation function. But from the physical point of view, what matters is the correlation function as a quantity describing the mechanism of the motion. I don't know whether I answered to your question.
It's now a bit more. Sorry, it's okay. It's okay.
Because then you have to decide, you see, because I was also giving this kind of lectures. So for instance, I derived from scratch the BPP formula. And some people liked it, sometimes thought that this is really of not much sense because you represent different disciplines and actually you do not want to know what it comes from. You only want to know whether you can use it and until which conditions. So we can discuss whether you want to go in this direction. It's up to you.
Okay, thank you.
Is there more questions?
Yeah, hi Danuta. I'm Mikhail. I have one question to you. Thank you for your lecture.
Thank you.
You said that your results is sensitive for the kind of molecular motion. And what about the non-uniform distribution of space distribution? Maybe clustering of molecules also have some different kind of your curves.
They do. And there is again the form of the correlation function or consequently the spectral density. I did not go to this direction at this stage because I just wanted to focus on the principles. However, how to describe heterogeneous motion or formation of clusters? Well, one applies a distribution of correlation times. Yeah. then the distribution must have some parameters. For instance, you can, and it's largely relies on ad hoc assumptions. For instance, you assume that there is a Gaussian distribution of correlation times. So Gaussian distribution has two parameters, and you have two more parameters to fit, and it fits or it does not fit. Yeah, people quite often assume the so-called Kohlrausch distribution, which is very, very controversial thing and completely not physical because it does not converge at low frequencies, but nevertheless people do. But this is again a kind of separated subject. Instead of, for instance, a single correlation time like tau c in this simplest relaxation formula, one could use a distribution of correlation times. Yeah, so for instance, you have a superposition of contributions with different correlation times weighted according to the Gaussian distribution. Whether it indeed reflects what is going on in the system is a big story, because it's like that. One has a relaxation dispersion profile, and one cannot fit it in a simple way. Whatever you do, you somehow cannot get a nice fit. It happens. And actually, our knowledge is also limited. Please do not take it personal. There's nothing just to you. Actually, we are not able to know everything about quantum basics of the relaxation, that, for instance, there are some other nuclei and they can affect the profile from quantum mechanical point of view, which is a completely different story. So if one is not really like spending years in this business, you just cannot fit the data. Okay. So usually it's like that, that if you have more parameters, you more likely will find a fit. So people say, no, okay, there are some interactions, maybe there are some clusters, maybe the system is heterogeneous. I'm not saying that it is not. So let me introduce a distribution of correlation times. I have at least two more parameters. I will play in this way. Oh, I got the fit. Yeah, but usually more parameters means that it is easier to get a fit. But this has a deep implications, because it's not that one finds some parameters. One claims that the system is heterogeneous. So this is a kind of major statement, and the question is whether it is true. So I would say that one should first explore and exploit all other ways of reproducing the data before one jumps to such conclusions. But mathematically, you can introduce a distribution of correlation times.
Yes, thank you. Thank you.
Yeah. So if there's no more question, please tell me, would you like to have this 15 minutes demonstration of something? Yes?
Yeah, that would be great, I guess.
Okay. And I'm sorry again for starting late, but I was really confused by the time.
It's okay, no problem.
Okay, so let me start again. And actually, there's a Kantman from Kayseri at this moment in my lab, and we collected some data. So with the permission of all people involved, I would like to show you examples of those data and some effects. And then I will send you software which we started to create. Actually, it's not software, it's a kind of Excel sheet, but you might find it useful. So let me start sharing again. Okay, I will close this thing. Oh, I do not know how to get rid of that. Just a moment. Just a moment. I have to close this. I have to close this. I will first have to open something, and then I will start sharing screen. Okay, and now I will start sharing. Okay, do you see my screen now? It's origin file. With pectin, 20% of pectin dissolved in water at different temperatures. You do not see much. Changes with temperature, although one should note that we have here logarithmic scale. But what the first observation which I would make is that here the curves goes up. This can be caused only by paramagnetic admixtures. So I would strongly propose to perform ESR experiment because we should see something. Yeah, because here it goes up, obviously. However, okay, let us.
And sorry, Danuta, so does that an indication about the paramagnetic impedance?
Yes.
Okay.
Because it goes up, I mean, clearly, yeah.
I remember in some other data, we observed such a pattern in the low frequency range. Is that also possible for the paramagnetic impedance?
No, in the low frequency range, I remember also the story, and we were fighting with the reviewer, and eventually she gave up, saying that, okay, it's a kind of complex phenomenon to be discussed later and by. But then we tried to explain it in a kind of effect which was called bipolar relaxation enhancement. We were saying that there are residual bipolar interactions.
Okay.
But then the residual dipolar interactions to get such effects have to be comparable with the Zeeman coupling. And of course, the residual dipolar coupling cannot be very large. So if you observe it at low field, it might be so, but definitely not at high field.
Okay.
Okay, but we got this thing. Now, okay. So the first thing which I would try is to take one of them. And I will copy it to a separated workbook. I'm using origin actually here. I will remove this thing. And here I have the resonance frequency. Here I have relaxation rate. So let me see the first test, whether maybe I observe translation diffusion, and whether the translation diffusion is isotropic. I don't know what will happen, but I would propose to do it like that. Let me change the X column, which describes frequency, to square root of frequency. So column, set column values. I'm changing this to square root of frequency. Okay, I did. So let me now plot this thing. Okay, plot it. Let me start from 0. I have here, frequency. Sorry for doing it so fast. Power 2, power 0.5. Of course, hertz power 0.5. Sorry for writing it in so inelegant way, but I want to make it fast. Okay, and here I have spin lattice relaxation rate. Yeah, I'm trying to make it fast. Now, okay. It seems like I have here indeed a linear dependence. However, nobody knows in so large scale. So let me enlarge it. Yep. Okay. This is not what I wanted. Sorry. Oh, okay. Let me look here. I will change it. So you'll see a little bit the scale. Okay, so still, I can still enlarge. Okay. Here. Here I can again maybe change it. Let me make it 50. Okay. So I see something. Whether it is linear, at least to some extent. But of course, this is not how I solve the problem. But it indicates that indeed, probably, that I see as one of the relaxation contributions, I see water translation diffusion. I mean, one of the reasons of the relaxation contributions, I see translation diffusion of water, and moreover, the diffusion is isotropic. Because indeed, I see a kind of linear dependence. You see, you have to be careful, because it can happen that, I mean, if the range is sufficiently narrow, it always will be linear. But here, okay, it's narrow, but not so. There are several points here, and I think one can indeed say that it's not accident that they form this pattern. So in such a case, let me select approximately the range, and I will fit the data. So I performed linear fit. I can make it like that. So you see it better. Yeah. So I fitted the data. And here I have slope. It does not matter that it has minus. Because it only says that the curve goes down. The value is important. Okay, so I keep it in mind. And now I can open again the presentation. The presentation. When you have this expression, this one, which links the diffusion coefficient with the low frequency slope via a series of expressions. However, here the expressions are pretty simple. This thing is easy to calculate. This thing is also easy to calculate because it includes well-known physical constant. So is this Planck constant is zero magnetic factor of protons. And here is vacuum magnetic permeability, which is also a well-known physical constant. The tricky thing here is a quantity which describes number of hydrogen atoms per unit volume. Because it seems that to get the translation diffusion coefficients, one must be able to calculate the number of hydrogen atoms per unit volume. Okay. This will be our next worry. At this moment, I determine the slope, and I would like to share with you a certain software. There's just here a thing And it's nothing else like just Excel sheet. Here is the well-known physical constants. Here, here, and here. This is something which I called product 1 and product 2. And it corresponds to product 1 and product 2, or another way around. Yeah, you can easily figure out what is what. Okay. And here, actually, okay, here is in addition this strange quantity calculated. Yeah, this thing, whatever. This you can easily figure out. And everything what you need to put here is the slope and the number of hydrogen atoms per cubic meter. And the slope, I already put, where's this thing? Here. The slope I already put. So I put the slope here. And, well, I can put something else. And here the diffusion coefficient is calculated. Let me, it was like that, I suppose. I do not remember exactly. 3084, yeah. Provided I know the number of water protons per cubic meter. And now is the question, how to calculate, because this is a kind of artificial number, yeah? How to calculate, it's not the correct one. How to calculate it? Here what I have, I know the composition of the sample. So let me just give you a kind of tips how to calculate this thing. If, let's say, if I would have just a simple sample, if I would have, for instance, such a thing, for instance, glycerol. We need two quantities, molecular mass and density. I suppose it's like that, glycerol. I don't know. No, it's glycerol. Molecular mass, just a moment. Okay, so I was right, it's glycerol. And we need molecular mass, molar mass, I'm sorry. Our molecular mass does not matter. It's in fact the same. And density. So who of you could give me that? Let me search. Let me search. Glycerol. Yeah. 92 gram per mole. 92 gram per mole. Let me search.
126 is the density.
126, okay. Density is 1.26 gram per cubic meter. And what is the structure of glycerol actually? glycerol, yeah, this C3 is just this structure. Yeah. So it's eight hydrogen atoms per unit volume. And I think in this way. Just a moment. 1 cubic centimeter means 1.26 gram. Yeah. It means 1 cubic centimeter includes 1.26 divided by 92 mole. Yeah. I calculated because 1 mole is just 92 gram. So let me calculate it. Let me calculate it. So it's 1.26 divided by 92 is more or less 1.27 times 10 minus 2 mole. I suppose so. Yeah. Am I right? Or not? Could you please calculate with me? So this means that in 1 cubic centimeter, I have this number of moles. So I have to multiply it by Avogadro number. So this is the number of glycerol molecules per 1 cubic centimeter. And if I want to have the number of hydrogen atoms, I have to multiply it by 8 because I have 8 hydrogen atoms per unit volume, per molecule. So now let me calculate it. So again, so I have like 1.37 times 6.02.8. So it's about 66 times 1021. Approximately. Does it agree? So, yes. So per 1 cubic meter, I can write it like that, is 6.6 times 20 power 22. So per 1 cubic meter, I will have power 29. Yeah. So if I would get such a slope for glycerol, it would be here. and I will have diffusion coefficient. Of course, as I have this system, I have to calculate the number of water molecules per unit volume in this case. There are protons also from pectin, but we are interested in the water dynamics. So I have to do some calculations, and this is already what I ask my group to determine the density of the sample after performing the solution, because one can hardly guess what the density is. So knowing the density and knowing the composition, we'll be able to calculate the number of water protons per unit volume. And then from such analysis, one would be able to get using the diffusion coefficient. If you want me, I can now send this to you. So let me do that. And now I can go to chat and I will find this thing.
Danuta, I have a question.
But do you want me to send this thing to you?
Oh, yeah, okay.
So let me send, and then I will do whatever you like. Okay, and now I will send it. Does not want to. That's it. I will send it to you, and maybe you can put it on the web page or somewhere.
Oh yeah, we can do that. We can take care of it.
Okay, so I will do that immediately after.
Okay.
Okay, so what can I?
Yeah, my question is, so this diffusivity that we calculate here, is it supposed to be similar to the value, let's say, if we perform a stimulated echo experiment to measure the diffusivity by a benchtop NMR?
It should be exactly the same.
Okay.
It is.
Okay, so this is the same diffusivity. Okay.
This is exactly the same because diffusion is like it is, but yeah. I mean, with the accuracy of factor 2, because we have this relative, yeah. But if we divide it by factor 2, it depends actually how this. But actually, this is here divided already. So in the Excel file, you should get exactly the same.
Okay. Okay. Thank you. And I think we are almost to the end of our time for today.
Sorry again, if you would be interested in analysis of real data starting from this point, I'm ready to do that in 2 weeks and I will be not late.
Thank you very much, Danuta.
Thank you.
We appreciate. So we will continue with our seminars. You already are informed about the other dates. So we have 2 more on data analysis as well. Thank you very much all for your